Today we're going to evaluate an infinite sum, which turns out to be a special case of a nice family of infinite sums, which we'll maybe explore another case of and leave you with some problems to think about on your own. So for us today, we'll mostly be looking at the sum as n goes from 0 to infinity of 1 over 9n squared plus 9n plus 2. And we'll use the following two main tools to evaluate this sum. So the first one is the sum of a geometric series. So if the absolute value of u is less than 1, we have the sum as n goes from 0 to infinity of u to the n as 1 over 1 minus u. And then next is related to the power rule from Calculus 1. So if r is not equal to minus 1, or maybe we should say really we need r to be bigger than 0 here, I guess, then the integral from 0 to 1 of x to the r dx is equal to 1 over r plus 1. Okay, so now that we've recalled those, let's get to this. So the first thing that we'll do is try to factor that denominator. And if you look at this, the denominator actually does factor quite nicely as 3n plus 1 times 3n plus 2. But now looking at that and thinking that sums are fairly similar to integrals, we'd like to maybe see if we can apply integration techniques to simplify this sum. And the integration technique here would be partial fraction decomposition. So in particular, what we'd like to do is take this 1 over 3n plus 1 times 3n plus 2 and rewrite it as some number a over 3n plus 1 plus some number b over 3n plus 2. So in order to simplify this, we'll take this entire equation and we'll multiply it by 3n plus 2 times 3n plus 1 to clear the denominators. So what is that going to leave us with? So we'll have a 1 on the left-hand side of the equation, and then we'll have a times 3n plus 2, and then b times 3n plus 1 on the right-hand side of the equation. But now let's see, that's going to give us 3a plus 3b times n plus 2a plus b equals, I'll write it as 0n plus 1. And now we can equate the coefficients of n from both sides of the equation, as well as the constants from both sides of the equation. So that means 3a plus 3b is 0, meaning that a equals negative b. And then from plugging that in here, we have negative b equals 1, which tells us that b is equal to negative 1 and a is equal to positive 1. So that means we can rip this apart into the sum as n goes from 0 to infinity of 1 over 3n plus 1 minus 1 over 3n plus 2. And we can't break those into two separate sums because both of those diverge by a comparison with the harmonic series. That being said, we can use our second tool down here to rewrite each of those as integrals. That's exactly what we'll do. So I'll take this and I'll rewrite it as the sum as n goes from 0 up to infinity. And then I have the integral from 0 to 1 of x to the 3n minus x to the 3n plus 1. Okay, great. And then dx. So the first term will give us this 1 over 3n plus 1. The second term will give us that 1 over 3n plus 2. Okay, now we're going to exchange the order of summation and integration, which is possible by something called the dominated convergence theorem. But this essentially always works when we have things that look like geometric series, which is what we have right here. So I have the integral from 0 to 1, and then I can factor an x to the 3n out of this, and that'll leave me with 1 minus x times the sum as n goes from 0 to infinity of x to the 3n and then dx. So just see if we divide out an x to the 3n from this term, we get a 1. Divide it out from this term, we get an x. So we're good to go there. And now we can apply our geometric series summation rule for this sum which has been left over. And so here, the role of u is being played by x to the 3n, so we know this adds up to 1 over 1 minus x cubed. Again, because the role of u is being played by x cubed. Okay, so that's going to leave us with the integral from 0 to 1 of 1 minus x over 1 minus x cubed dx. But next up, there's a standard factorization for difference of cubes that allows us to factor this as 1 minus x times x squared plus x plus 1. And then this 1 minus x will cancel with this 1 minus x. And that leaves us with the integral from 0 to 1 of 1 over x squared plus x plus 1 dx. So we have something like that. So now let's bring that up here and we'll finish this first example off. So this is where we left ourselves off. We have our sum is equal to the integral from 0 to 1 of 1 over x squared plus x plus 1. Now we'll take this x squared plus x plus 1 and complete the square. So let's see, that'll give us the integral from 0 to 1. We'll have 1 over x plus 1/2 squared and then plus 3/4. So let's talk our way through that. So if we multiply x plus half times x plus half, you'll get x squared plus x plus 1/4. Add that into the 3/4 and we get 1. So we're good to go there. Okay, so next up, I'm gonna factor some stuff out of this denominator so that it looks a little bit nicer so we can make a nice substitution. So I'll divide a 3 over 4 out of the denominator, which is the same thing as dividing a 4 over 3 out of the whole thing. And then that'll leave me with 1 over. So this bit that's in the square is a little bit tricky. I'll write it down and we'll talk our way through it. So this is 2x plus 1 over the square root of 3 quantity squared plus 1 dx. Great. So when I take this 3 out of the denominator, that means I need a square root of 3 inside of this square. And then taking a 4 out of the denominator is the same thing as multiplying this term by 2 squared, but then since we've got this is already squared, it just turns into 2. Okay, so we've got something like that. So now we'll make a substitution, and the substitution in question will be t equals 2x plus 1 over the square root of 3. So that tells us that dt is equal to 2 times the square root of 3 dx, or in other words, dx is equal to the square root of 3 over 2 dt. Okay, so let's put a box around this, and then that will go through and substitute in for this red box. And then we'll put a purple box here, and that's going to go in and substitute for this purple box. Now let's see what happens to the bounds of integration. So if x is equal to 0, that tells me that t is equal to 1 over root 3. And then when x is equal to 1, that tells me that t is equal to 3 over root 3, which is the same thing as the square root of 3. So let's see where that leaves me. That's going to leave me with 2 times the square root of 3 over 3 times the integral from 1 over root 3 up to root 3 of 1 over t squared plus 1 dt, after doing some simplification with the arithmetic. Okay, but applying the fundamental theorem of calculus, that'll give us 2 root 3 over 3, and then we'll have the arctan of the square root of 3 minus the arctan of 1 over the square root of 3. But now we can apply this arctangent difference formula to this stuff that I'm underlining in green, which Justin will put on the screen right now to remind you. That will allow us to simplify that stuff quite a bit. So this will give us 2 times the square root of 3 over 3, and then we'll have the arctan of 3 over root 3, that's the same thing as the square root of 3, minus 1 over the square root of 3, all over 1 plus 1, which is 2. But then after some simplification, you will see that this inside, the argument of the inverse tangent is the square root of 1, or 1 over the square root of 3. But the arctan of 1 over root 3 is pi over 6. So that means we have 2 square root of 3 over 3 times pi over 6, which in the end will give us pi times the square root of 3 over 9 as our final answer. Okay, so now that we've got a feel for how this goes, let's look at another one really quickly. So for our related example, we'll look at the sum as n goes from 0 to infinity of 1 over 6n plus 1 times 6n plus 2. So I'm going to skip some steps, but the first couple steps that we did on the last problem brought us to the following spot fairly quickly. The sum as n goes from 0 to infinity of the integral from 0 to 1 of x to the 6n minus x to the 6n plus 1. Of course, we skip that partial fraction decomposition and stuff like that. And then I'll skip some other steps, which are very, very similar to what we had. And we'll have the integral from 0 to 1 of 1 minus x over 1 minus x to the 6th dx. Great. But now let's factor 1 minus x to the 6th. So 1 minus x to the 6th. And let's keep in mind that this can be thought of as maybe something like x cubed squared. So we can factor it with the difference of squares. That'll leave us with 1 minus x cubed times 1 plus x cubed. And now we can factor each of those using a sum of squares and a difference of squares. We'll have 1 minus x times 1 plus x squared times 1 plus x, and then 1 minus x plus x squared. So we have something like that. Notice we've got a 1 minus x in the denominator, so that will cancel out and leave us with the integral from 0 to 1 of 1 over, let's see, 1 plus x plus x squared, then 1 minus x plus x squared. Great. And now we'd like to do partial fraction decomposition to simplify this. Notice we've got these two extra terms which require some simplification. So again, I won't work through the details, but I will point out that when you do the partial fraction decomposition, you have to have a linear term on top of these irreducible quadratics. So that's going to leave us with something like this. 1/3 the integral from 0 to 1 of 1 over x plus 1 dx. And then we'll have plus 1/2 the integral from 0 to 1 of 1 over x squared plus x plus 1 dx. We just saw that integral, so that's kind of nice. And then minus 1 over 6, and then the integral from 0 to 1 of 2x minus 1 over x squared minus x plus 1 dx. And now it's just a matter of calculating the values of each of these integrals. And what I'll say is that this last integral has a value of 0, which again, like I said, you guys can check on your own. And then this first one is not too bad. It's just the natural log of x plus 1 evaluated at 1 and 0. That'll give us the natural log of 2. So in the end, this will be 1/3 times the natural log of 2. And then this is going to be a half times our previous result. So in the end, that'll be pi times the square root of 3 over 18. And that gives us our final answer. And then here's maybe my follow-up question for you, and that is to explore the following sum, which is maybe the logical generalization of these two. Maybe we could have 1 over an plus 1 times an plus 2. So some values of a make this nice, but some values of a make this very, very difficult to calculate. So maybe which values of a make this work out nicely? So maybe post in the comments if you find any other values. I think like maybe a equals 4 makes this work out pretty nicely, but I think some simple exploration could find a few more. Maybe, like I said, post in the comments what you find. And if you like these kind of summation problems, I've done several on the channel so far, and there should be one on the screen right now for you to check out. And that's a good place to stop.